This is what we had done in the last class. We discussed the model of particle in a box, which is a model to understand many of the things that happen in subatomic systems. Um, or in general, it is a translational motion that we are talking about. So this kind of translational motion, when a particle is trapped in a box, so we know that it is moving like this back and forth. So this is the kind of motion that we are talking about. The energy at the walls is so high, or that it is taken to be infinity in theoretical when we are discussing it, that the particle cannot penetrate this wall. It is so and inside, so potential energy is high up to infinity at the walls, and inside it is zero. But the particle will is moving, so it has some kinetic energy, and that's why when we write this term, the Schrodinger equation for such particle, v is 0 inside the box, and our equation gets simplified with this. And what we noticed last time also, it was uh, so it was this is the general type of solution for translational motion, in which can be fitted, which fits here in the Schrodinger equation and satisfies this equation. So this kind of, it is e to the power I kx and b to the power b into e to the power I minus I kx. So this kind of thing was so if we express this in terms of cos and sine functions, so it can be written like this, and then collecting all the terms, you can put it, give it a simplified expression, c sine kx d cos kx, like this. The sine function here is the imaginary one, that's it is has a I term, whereas cos kx is the real, so it is overall a complex wave function that we are talking about. And as we have seen, an important conclusion of in the previous section when we discussed the free motion, it was to show a net movement. It is essential for the function to be complex. It has must have some imaginary component with I. Otherwise, you cannot describe a net motion. So the energy of the system, as we know, if k is the wave vector, so k square h cross squared by 2m is the general feature, because kh cross is the momentum. So this is how we can general idea of energy we have, that for such equations. uh, uh, so potential energy is 0 inside the box. uh, so we first thing that what we did, we tried to find out the energy of the system and energy of the particle trapped in a box. So we had to design wave functions, and so we utilized this help, we took the help of this from the postulates that we have already studied in the first part of the quantum mechanics classes. So postulates 2 and 3 were important. Continuity of the function, the slope must be continuous, and also the boundary conditions are important. The boundary conditions here is that at the boundary the function must become 0. Particle is not to be found in the walls, so the function, the amplitude of the wave must go to 0. So wave function has to be 0 at the boundaries. So at when x is 0, when x is equal to L, in those conditions it should be 0. So this was the acceptable solutions that we found, that anything that you try to fit, so the green one is acceptable but the red one is not acceptable, because at the wall on one side, right hand side wall, you are seeing a finite value of the. So if we try to simplify, we try to fit based on these ideas, if we try to fit between the walls, This is the scheme that we get. Starting with the so what you see here, this is a very important thing. So it is when you take one half wave, two half wave, three half wave, or four half wave, it perfectly fits the container, satisfies all these points that we pointed, all the points of postulate 2, 3, and also the boundary conditions. And this is a general scheme that we can make out, that we have to fit half waves, one half wave, two half wave, three half waves, and so on. And this is so the number, each one corresponding to n is equal to 1, 2, 3. So this comes in our numerical calculations. So that is the that integer is called the quantum number, which defines that this is the possible wave function, and corresponding to it, it can have certain energy. This is another energy that is possible, but not any intermediate thing is like that. So this is the quantization, and this number defines the key aspect of quantization, that energy is not continuous, it can change only in this fashion. So that is the thing. So you also see the 2-3 points that you can see here. As n increases, the curvature is increasing. 2-3 points, very quick points that you can see through. बहुत सारी चीजें हैं जो इस डायग्राम में आप देख रहे हैं. Number one, you can see that amplitude as the function 1, and can I pause it इसमें. So number 1 जो था उसमें हाफ वेव है. Sorry. So as n increases, the number of nodes increases. Okay. So and you can see I told you that curvature means high curvature means high kinetic energy. So as you can see, 5, 6, 7, 8, gradually the curves are more sharper, curvature is greater, indicating that now the kinetic energy has increased much more. So 1, 2, gradually see the curvature is increasing, the bends, the sharp bends. So more are the nodes. There is so the function, when it tries to maintain the continuity, it bends sharply. Okay, and so the curvature is high, and that indicates the kinetic energy is also high, because it is a second derivative d2 psi by dx square, which is the curvature. So curvature, look at the curvature. Curvature is, this indicates related to kinetic energy. So higher curvature, so as n increases, the curvature is higher, indicating high kinetic energy. Initially n is equal to 1, no node, there is nothing. 1, 2, so number of nodes, if you see, gradually increases. As n increases, the function tries to maintain its continuity, the bends become sharper, the curvature is high, and that means you have high kinetic energy. One simple look, you can get that. So a trend that emerges is that you must be able to account for the length has to be kept same in all cases. So a trend is that here also it is equal to L, this is also equal to L. So the lowest energy situation, lambda by 2 is equal to L, right? Is equal to L. This situation, again 2 lambda by 2 is equal to L. This one, 3 lambda by 2 is equal to L. So a general trend that you see here, lambda is equal to 2L by 3. This gives you lambda is equal to 2L by 2. This one gives you lambda is equal to 2L by 1. So if you are noting this point, you are seeing a trend that is so the trend that you see 1, 2, 3. So this in general in general you can write that lambda should be equal to 2l by n, where n is equal to 1, 2, 3 and so on. So this set of integers define what kind of wavelength is possible for the wave to be fitted in this box. Okay, and that means if only these waves are fitted, only the energies, they can have certain value of energy as indicated by the wave, so they are associated with certain energy, so that is only possible. So the energy cannot change continuous manner, it can change only as indicated by this. This is the quantization that we are seeing over here. Energy is, so simple idea of fitting the waves, you are getting this thing, and now you can also extend this idea to find the energy, because k is equal to lambda, you have known k is equal to 2 pi by lambda. So when you have to write it, you can again correlate this thing. 2l by n is the lambda, so substitute it here, and k can be replaced with so in a simple way we can do this. K is 2 pi by lambda, we have just found that lambda is equal to 2l by n. So k, which implies k is equal to 2 pi by 2l by n. Okay, so k is n pi by l. So k square, you substitute this value of k in, so the energy of expression is p square k square h cross k square into h cross square by 2m. So substitute this value of k and you get the value of energy. Okay, so that is the so then if you do this, so all these things simply by fitting the, observe the general trend, generalize it, you find that it is 2l by n lambda, then use that lambda, equate it with things and try to get this h by lambda p square by 2m, so you can fit it and you can get the energy, which is easy to get define. So this is how we define so this is one way of doing this, a much simpler way, easier way, जिसमें कि बहुत ज़्यादा मैथमेटिक्स की ज़रूरत नहीं है, सिंपल लॉजिकल सीक्वेंस आपको पिक्चर्स के थ्रू दिख रहा है, उसी से बन जाता है. सेकेंड अप्रोच इज जनरल, एंड सेकेंड अप्रोच में आप पूरा वेव फंक्शन का इक्वेशन निकाल लेते हैं, कोफिशिएंट्स की वैल्यू निकाल लेते हैं, एनर्जी तो निकल ही जाता है. So second approach is to follow a more mathematical approach, which is uh, more formal in sense in quantum mechanics. So you first identify the boundary conditions. So you have when x is equal to 0, psi must go to 0. So substitute the value, first boundary condition, and find that x is 0, sin kx 0, sin 0 is 0, cos kx is equal to cos 0, 1. So that simply tells you that one of the coefficient has to be this goes to 0, whole function gone, only d remains, and d is equal to 0. So one of the coefficient becomes 0. So this is done. So because psi k is 0, so d is equal to 0. It follows the wave function now is only, it has to be only a function of sine, c sine kx. Now again you apply the second boundary conditions, and at the length L, the function becomes c sine k L, capital L, and the whole thing should be 0. So you cannot make c 0, because that would mean that for all values of x the function is 0. That's not true, that's not possible, because particle then is nowhere to be found. So a better way to think is, other alternative is that you make sine kl to be 0, and a condition must be there that KL should vary as a function, should be equal to n pi, where n is in an integer multiple of 1, 2, like this. So when we do this, then it becomes easier. And so in this case, n is equal to 0 is ruled out. You cannot have the n value cannot be 0, because then k will be 0 and psi kx will be 0 everywhere. So which is again unacceptable. So negative value is also unacceptable. So there is a total set of justification why we are saying that n can vary 1, 2, 3 in this manner onwards. It cannot be 0, it cannot be negative. So it cannot be negative because of this reason, sine minus x minus sine x. So this is not adding up to a new solution, so it doesn't make sense to add a negative value of n. Wave functions are therefore c sine. We are now substituting the value of k here, n pi by l, and that gives us the form of equation n pi by l. So this is okay. The next task is that evaluating the c. So now once you have k, you can substitute it here and get the value of energy is the same manner. So n square is, so this is this expression of energy which we are getting, which also obtained by the informal approach. And the informal approach that we had done by simply looking at the first function profile of the function, trying to fit the half waves in the box, and the two things are now matching up. Now the next task is to evaluate c, the constant coefficient, and that is done by presence. So boundary conditions were applied, and when you try to find the probability, you should be able to do this. So determining the c is a condition that we had. So we tried to find out this psi square dx integrated between 0 to L, it must be equal to 1. So when you do this and complete the integration part, you get the value of c. So this is also very simple, कुछ भी मुश्किल नहीं है अब तक. Final expression is this. So you got the final expression of the wave function under root 2 by L sine n phi by L in x. So this is the expression. This is what we had reached last time, and now it also goes indicates that. So this is the function, this is the energy labels. Now you can see that indexing is now in terms of n, not in terms of k, because we have replaced k with n pi by L. Okay, and it also means that because Hamiltonian is Hermitian operator, this also means that the wave function 1 psi 1 for the n is equal to 1 and psi 2 n is equal to 2, so these are orthogonal. That means if you the product of psi 1 psi 2 into dx should be over the integrated over the entire limits 0 to L should be 0. Okay, so that is also something that we can see from the area under the curve. So this one and this one, this is the product. So if you multiply graphically, then the product will be like something like this, psi 1 into psi 2. So and integrating over them over the area gives you 0. So now if you look at the expression is E is equal to you had n square by h square 8 m L square. So this was the energy. So plot this as a function of so if you look at what would be the separation if you define something, a scale on the vertically like this in the screen. So this is your energy, value of energy. So you can put n and see how it changes. For n is equal to 1, n square is 1, n is equal to 2, other things being constant, you can So it will change in this manner. For n is equal to 2 it will be 4, n is equal to 3 it will be 9, 16, 25, 36, 40. So what you see is that this is the thing, the energy is gradually, as n increases, the gap between subsequent energy levels, two consecutive energy levels, is also increasing. So it is just the number that you can see, 6, 7, so square of that is 49, 30. So the gap is increasing, increasing. So they are closer at the bottom, and as you move to the upper part of the energy level diagram, they are more farther away from each other. So this in the integer that we are talking about, this is the thing that was called as quantum number, because this is makes up the whole thing, that the energy has only certain allowed values, it cannot change continuously. So because it is an n square function, separation gradually increases as the quantum number increases. You can clearly see this happening, the separation here, separation here, separation here, separation here. So clearly the separation is increasing. So quantum number is integer in this case, and in some other cases we will see half integer will come. That will only the spin case, spin wave function, when we will write later on in the second semester, then we will see that half integer will come. But so far most of the time this integer is this is only integer values that we are seeing. uh, so the particle in a box, there is infinite number of acceptable solutions. So we can define, like you can see here, we in 1 2 3 4 10, so n can go up to infinity, and n specifies, so you can find the n that is your of energy of your interest. So now look at the functions, how they are plotted very carefully. So you have this psi on y-axis, so this is what has been shown. X is, it is the length along this length of the, so 0 to L, capital L, that we were showing, length of the box. So what, there are points to be noted. One, when n is equal to 1, one half wave you are fitting, so this is the n value of n, this, so value of n, and 5 up to 1 2 3 4 5 have been compared in this diagram. What you see here, so all the waves must become zero at the two boundaries when they touch the wall. Okay, so that's happening. Number two, all the waves have same amplitude, the amplitude is same. So n is equal to 1, this is the amplitude you are seeing, maximum. So amplitude of the waves, the maximum amplitude that you can see in any of the wave. So amplitudes are not changing, amplitude is same for all the functions. ठीक है, तो जब आप एग्जाम में ड्रॉ करेंगे इस बात का ध्यान रखेंगे, यू विल पे अटेंशन टू दिस फाइनर डिटेल्स दैट आई एम टॉकिंग अबाउट. All the wave function, when they have to be shown in a particle in a box, they will have to be drawn with the same amplitude. Okay, so आप देख सकते हैं नीचे देखिए यहाँ पे सब एक लेवल पे है ना, amplitude is same. Then what you see, n is equal to 1, you have maximum probability in the middle, but n is equal to 2, there is a node at that point. For n is equal to 2, you have a node at the point where in case of n is equal to 1, you are having maximum amplitude. So probability in the middle of the box is 0 for the psi 2 function, but for psi 1, so for psi 1 you have, for psi 2, which was this one, so psi 1 and psi 2, compare these two, what you see that probability, maximum probability. So probability is the square of the amplitude. So square, if you do the square of this thing, psi1 square is the probability, uh, is the density. So this is the probability, gives you probability density. So it is maximum for the in the ground state n is equal to 1. There is maximum probability for the particle to be found at the middle, in the middle of the box. But for n is equal to 2 state, when we are having this kind of wave function, this is the wave function for this particular state, the maximum probability is at the two ends, the two extremes, here and here, right? Probability here, where, and in the middle there is zero probability. So in this manner, if you move from this side to, just moment, ओके चल रहा है ना, हाँ रिकॉर्ड, यही बार बार चेक करना पड़ता है, कई बार पिछली कल गड़बड़ हो गया था एक बार, पता नहीं चला था. So these are the points that you see. So you can clearly locate from this graph, as n is, so 1 2 3 4 5, as the number increases, n value, the quantum number n increases, you have the curvature becomes sharper, so kinetic energy increases. So curvature becoming sharp, you can see 3 4, number of nodes increases, n is equal to 3, you have 2 nodes, n is equal to 2, you had only one node. So and by the time you are at n is equal to 5, you have n is equal to 5 is this one. So node is here, another node, 3 4, so 4 nodes for n is equal to 5. So 4 nodes, 1 2 3 4. So this is the so you can so n is equal to 1, no node, n is equal to 2, 1 node. So 1, so nodes keep on increasing as the function, uh, as the quantum number increases, the curvature increases, you can see the number of nodes increases. To maintain the continuity, the function becomes more curved, more, you have a sharper curvature, which uh, in a mathematical sense is the second derivative of the function d2 psi by dx square. So kinetic energy is increasing. So these are the things that we have observed, and these are the points that would be, you'll find written on the slides for your notes purpose. They are, so they are all sine functions. This is what we know now, with the same amplitude. Sine function with the same amplitude. This is the wave function of a particle in a box. Simple. Sine with same amplitude, but different wavelength, right? This is what we get to know. Number 2, they are all standing waves. They are not going anywhere, right? और यही मैं आपको इलेक्ट्रॉन्स के बारे में शुरू में समझाया था ऑफलाइन क्लासेस में भी. We have to treat, whenever electrons, we treat electrons inside an atom, we treat them as standing waves, right? So बहुत इंपॉर्टेंट है, सिग्निफिकेंट पॉइंट था वो, क्योंकि स्टैंडिंग वर्ड गायब रहता है. आप इंडियन ऑथर्स की कई सारी बुक इलेक्ट्रॉन्स के बारे में पढ़िए, पता नहीं चलेगा कि सिर्फ आप वेव मैकेनिक्स आपको याद रहता है, श्रोडिंगर वेव, लेकिन स्टैंडिंग वेव का इम्पोर्टेंस क्या है वो नहीं पता चलता. लेकिन ये कितना इम्पोर्टेंट है आपको पता अब चल रहा होगा. So it is a standing, so anyway, so this is a general scheme of any moving particle. Each wave function is a standing wave, and successive functions have one more half wave and progressively become shorter. Shortening of wavelength, sharper average curvature, increasing kinetic energy, all these points I have just mentioned 2-3 times already. And number of nodes you can see increases, n minus 1, psi n has n minus 1 nodes. Linear momentum of particle is not well defined for any function which is having sine kx, is because sine kx not an eigenfunction for momentum operator. So this is something you should check. This is sine kx, cos kx, which one is eigenfunction for momentum operator. You should take it as an exercise, do it. Okay, so linear momentum is not well defined because of directly it is not possible to find out, but you can think of it as superposition of two functions like this. Sin x can be represented by e to the power ix, e to the power minus ix by 2i. So in this, so by Euler theorems, again you can transform it into this way and say that it is a superposition of two waves. And psi n we usually write by this. Now we can, if we are putting it in this way, so sine x will be replaced by the terms like that 1 by 2i coming over here. So it is another way to write the same function, and which means that you have possibility of getting the both kind of, now these two are eigenvalues, eigenfunction for the momentum operator. Now it becomes each of these two functions are which are now superimposed to give you the sine kx is now the function eigenvalues can give you. So both possibilities are there with equal possibility that either the particle is, you one time you will get plus kh cross and another time you might get minus kh cross. So if you do a large set of measurements, you can have both the things can happen. And so that means that it is so there's equal probability of the particle to be moving left or right. Okay, and this is in the classical sense, this is what we mean by a ball is bouncing between two walls. So एक बार, so that is called rattling motion. इधर से उधर rattling word मैंने पहले भी यूज किया था ionic bonding में, जब मैंने कहा था कि वो छोटा हो जाता है ना, डिमिटिंग रेशियो छोटा केटायन होता होगा तो वो होल के थ्रू बैक एंड फोर्थ ऐसे अंदर बाहर वो अप डाउन मूव करता रहेगा साइडवेज, तो उसको रैटलिंग मोशन का सेम रैटलिंग मोशन यू कैन थिंक ऑफ particle moving back and forth bouncing between two walls. So if it is doing this, then it is spending half of the time traveling to right, half the time traveling left. And lowest possible energy n, as we discussed there, n cannot be zero, we have discussed previously, and that means the lowest possible energy is h square by 8 ml square. uh, so that is so which also means that this is the minimum amount of energy that will always remain with the system. It, the energy of the system, even if whatever you do, you reduce the temperature or anything, it is the bring it to 0 Kelvin, even then some energy of this amount will remain with the system, and that is called 0 point energy. The this lowest possible energy which is irremovable, that is called 0 point energy. इरिमूवेबल, रिमूव करने के लिए क्या करते हैं यूजुअली हम लोग, क्या करते हैं, अगर कूल करते जाएं तो एनर्जी कम होती जाती है पार्टिकल की, एंड फाइनली वी सपोज दैट एट 0 Kelvin everything should stop, no motion should be there. But this is one example where you have the energy cannot go to zero, there will be some amount of energy associated with it no matter whatever you do. That's why we say that it is irremovable energy, and we call it 0 point energy. Okay, so the physical, you can argue this, justify this in two ways. One is by applying Heisenberg uncertainty principle. So we know that particle is located within the box, or another way is saying that the uncertainty with the is location of particle is not completely infinite. That's another way of saying the same thing. That means uncertainty with associated with position is not infinite, and that means the uncertainty with momentum cannot be zero. Okay, so momentum, if momentum is not going to be zero, that means it must possess some kinetic energy. If momentum is uh, and so it will always have a non-zero kinetic energy. So the way we have defined this terms, now you know this in terms of expectation values, the uncertainty in momentum is defined in this ways. So in this case, del p is not equal to 0 implies that this p square term, which is particle, must always have non-zero kinetic value, kinetic energy in this case. So that is something, yeah. So you have, so you see in this particular box, when the box it is moving back and forth, this term, the averaging of this will be, this term may go to 0, but the first term is not going to 0. Okay, and so that means that p square, this expectation value of the square of the momentum is not 0. That means the particle must always have some non-zero kinetic energy. So this is how the reason that why this 0 point energy will remain. And so then you can think of in another way. Second point of view is that the wave function is going to be 0 at the walls, but it has to be smooth, continuous, and non-zero everywhere else. So it must be curved. If so, the design of your function is something like it will be curving 0 at the two ends, but having a curvature after that, just after that. So if there is any curvature in the function, there must be a kinetic energy. Okay, so from this point of view, the you can explain why 0 point energy is there. Okay, the separation. So if you now try to work out the separation of the energy levels, so n and n plus 1, compare them. So n plus 1, substitute that value, h square, h minus, subtract this thing, so you get this. Okay, so this is of considerable significance, because now using these functions you will be solving many problems related to the uh, energy levels in a molecule, having a linear chain molecules, like having a delocalized electrons throughout the chain, highly conjugated, so that can behave like this one-dimensional box. And this conclusion will help you in doing those things. So as the separation, so what you see here, as the separation increases, as length of the box, if suppose the length of the box is increased gradually, what will happen, they will the energy gap will decrease. And if they are, suppose you are approaching infinity, if you are separating, length becomes infinite, at very large distance, separation will be so less that it will appear to be changing continuously. So you will have a situation that normal classical picture emerges from that. If the length of the box is very big, infinite almost, then separation will becomes zero, almost zero. Okay, so infinite separation, infinite length of the box, if that is, if L is infinite, this del E becomes 0, and then that means you have a continuously changing energies. The energy can change continuous manner. So that is the thing. So when you are talking about a molecule in in a beaker, suppose I have a water molecule, one water molecule in a beaker, and it is I can say that it is like a particle in a box. It is moving back and forth in this. So what will be the energy? So for the molecule, that length scale in few centimeters is almost like having a infinite wall. उसका कहाँ एंगस्ट्रॉम में होगा 10⁻⁻10, आपका सेंटीमीटर में बहुत ह्यूज डिफरेंस है. So that scale is almost like having a, it sees the molecule, उस molecule के लिए वो infinite distance की तरह ही हो गया चलना. Okay, so in that case it will see the kinetic energy of that particular molecule will be like translational energy, which is not quantized. We treat it as like this. So that is a conclusion, that one conclusion considering the length. Similar conclusion you will get when you at very high quantum numbers. Okay, that is coming up next. We have completely free particles is not quantized. We have already seen in the free motion that we considered first. And now how to apply these concepts in your daily scheme of things when you are working with system. So this is what, this is carotene. Carotene जो गाजर में खाते हो ना, गाजर में जो होता है वो यही होता है. C22, 22 carbon atoms is there, and it's a highly conjugated structure. 22 carbon atoms सबके, so p orbital of 22 carbon are overlapping, forming a huge molecular orbital. एक लंबा सा molecular orbital बन रहा है, उसमें इलेक्ट्रॉन लेफ्ट से राइट, राइट से लेफ्ट घूम रहा है. सो सोचो ये एक पार्टिकल इन बॉक्स की तरह ही मॉडल है, उससे बाहर नहीं आ सकता, उससे फंसा हुआ है, ट्रैप्ड. So the length of the molecule is CC bond length is 140, and length of the molecular box you can treat it, you can calculate to be 2.594 nanometer. Now you have to calculate what will be the, if it is in ground state, and next you want to excite it, what is the energy, the wavelength of light that you require. So how will you calculate? So you note the point, each carbon atom contributes 1 p or electrons to the pi orbital. So you have to find the uh, orbitals which is HOMO and LUMO. You have to find the highest occupied orbital, and if there are n is equal to 11, you will form each one contributing so they are, each contributes 1 p electron to the level, so each level up to the 11 is occupied by 2 electrons. ठीक है. So you go filling up the orbitals, molecular orbitals, so 2 2 2, so 22 carbon atoms contributing, so up to 11 it is completely filled. And then the next between the highest occupied and lowest unoccupied levels, convert that energy to a wavelength. So the transition that you have to work out is n is equal to 11 to n is equal to 12. So this is the highest occupied orbital that you can think of. Okay, so 11 orbitals, 22 carbon atoms, 22 p orbitals. So 22 atoms, if you have 22 orbitals combining, you will get 22 molecular orbitals. Half of them will be bonding, half of them anti-bonding. So when you start filling the electrons, you have 22 electrons to fill up. So first 11 orbitals are filled with 2 electron each. So n is equal to 11 level becomes your highest occupied molecular orbital, the pi, due to the pi overlap. And the next n plus 1 is 12. So this is the transition that we want to locate, we want to find out. So this is something you substitute and find out. So this is the thing that you have to do. Substitute 11 n, and n plus 1 becomes 12, and then calculate. You are here, so this is something you will do it, find out. So this is the del E, it should be equal to h mu, and so mu is known, you can find out the wavelength, frequencies. In a similar way you can do it yourself. you have a typical nuclear excitation. Similarly, you can apply it to any system. 1 electron volt is now joules. Calculating first excitation energy of a proton confined to a square well with a length equal to diameter of nucleus. So here also you can apply this, and you can, so length of the box, diameter of a nucleus is given equal to the diameter of a nucleus, which is approximately 1 femtometer. Okay, so that is, again you can do this. So now we turn our focus on the probabilities that we can find out. So this is here, there are two functions plotted for the particle in a box. So what you see here, again note these points. N is equal to 1. Yeah, so when you square it, the function is given. When you square it, a normalized wave function, if it is squared, that gives you psi square. So this is psi 1, and this is psi 1 square. This is psi 2, and this is psi 2 square. Okay, so this is the blue curve, and the red curve, psi 1 psi 1. So the bottom graph shows you the square of function. So blue, where it was negative, it is now shown with a positive line. So this is what you see in the second wave function psi 2. So you are clearly seeing now that having a maximum probability at the psi 1 square, maximum probability is at the middle of the box. Psi 2 square has a maximum, maximum probability here and here at the both ends, but not at the center. So mhm, the wave functions that you see, and okay, so probability density for particle in a box is, you can have to square the function. So squaring the function, root 2l square of it, 2 by l sin r squared and pi x by l. So this is your function. Now what you see, probability density is changing with the position. One thing that you see here, that probability changes with position clearly. N pi square kx. Pictorially you can see, if you look at the equation, you can see both the things happening. Position will change with the probability will change with respect to position. So non-uniformity is also pronounced when n is small. uh, so you can see the first one has the maximum probability in the middle, and then other side is less. So not, it is not to be found on the sides, but only in the middle portion of the box, that is at the lower energy. But when you go to n is equal to 2, you have equal probability on both ends. And as you go to n is equal to 3 further, the one that we have seen, if you think of the previous curve that we had here, yeah, this one. So remember this curve, n is equal to 5 was plotted. So look at the n is equal to 5. If you square this, you will get the probability for finding the particle when it has energy corresponding to n is equal to 5. So it will have probability here, the square of this function, it will be also here, third here, fourth here. So you will have many points where it will have equal probability of being found out. So, and if you go to further high, increase the n value, you will get many more points where the probabilities would be similar. So that is the point, that initially what we are saying, that initially at the lower value of n, you are having more non-uniformity of the probability distribution. When you go to higher value of n, the distribution is becoming uniform, more uniform, ज्यादा यूनिफॉर्म होता जा रहा है. क्या? हेलो. Hello, who is it? So non-uniformity is pronounced when n is small, and later on it becomes more and more uniform as n increases. You can clearly see this. Who is that? Can you switch off your mic? Can you switch off your mic? Pampa. Okay, so uniformity, probability distribution density becomes more and more uniform with respect to x with distance as at higher quantum numbers. When n increases, this no, probability density, and you have more points where you have high probability of finding the particles. The distribution is becomes so at very high quantum numbers, almost all the points will look like as if they have uh, equal times at all points. ऐसा भी situation आपको लगेगा. So when you go to the high quantum numbers, there's almost equal probability of finding the particles at different points. So that is also a result that is we find in a classical picture, that if a ball is rattling between two walls, there is equal probability of being finding the ball at any position, any value of x. So that is a classical result. So at high quantum numbers, again this is showing. So this is the who is that? कौन है? So this is the power, yeah, equal times at all points. So you can see here, you have so this is the wave function psi1, and this is the psi1 square. Psi1 square. This is psi1, psi2, and this is the psi2 square. Psi3 and psi3 square. So you can see this, what is happening. So clearly, so this is what I was telling, that probability only here one point, high probability point is this one. Now you have 2 points of this equal probability. At these 2 points you have here and here equal probability. Okay, now look at the n is equal to 3. So you have 3 points of equal probabilities here, here, here. And this is what I am telling you, that if you go on increasing the number n, the quantum number increases, the point of equal probability are becoming a more in number, and they are closer to each other. So finally a situation may come that you will have almost all the points at say n is equal to 20, n is equal to 25. You will have such a large number of points where there will be equal probabilities, and the distribution will look like uniform distribution. Particle can be found anywhere at any given point. So that is a classical result. So at high quantum numbers, we are able to correlate with the classical results which are shown by classical mechanics. So this is again the correspondence principle that we can think of. Okay, so we will discuss the two-dimensional motion in the next class. This will be particle in a two-dimensional trapped in a two-dimensional square well. So this will be the we will do in the next class. So that's all for today.